This is lesson 14.1. Our objective today is to be able to apply the Pythagorean Theorem and find unknown sides of right triangles, and also to be able to determine whether three sides of a triangle make it to be a right triangle or not. The supplies you'll need is a piece of patty paper and a straight edge. Straight edge is kind of optional, but you definitely need the piece of patty paper for an activity that we're going to be looking at. Most of today's lesson will be a review. This is an 8th grade standard as well to understand and apply the Pythagorean Theorem. We're going to get a little bit deeper with it in geometry and look at several proofs of the Pythagorean Theorem as well. So first of all, in order to be able to apply the Pythagorean Theorem, there's a couple of background pieces of information that we need to make sure that we understand. Remember, for a triangle to be classified as a right triangle, it has to have one right angle. So a right triangle is a triangle with exactly one right angle. Remember that the three angles of a triangle have to add up to be 180 degrees, so there's no way you can have more than one right angle. If you had two of them, that would add up to be 180, and you wouldn't have any degrees left for the third angle. So how can we classify right triangles? By the side lengths. So when we say it's a right triangle, we're classifying it by its angle measure. Remember, there's three ways to classify triangles by their side length. Either all three sides can be different lengths, which we call a scalene triangle. At least two of the sides can be congruent, which we call an isosceles triangle, or all three of them can be congruent, which we call an equilateral triangle. Well, since a right angle has to have one right angle, or a right triangle has to have one right angle, we know that all three of the angles cannot be congruent. They can't all be 90 degrees. And equilateral triangles have to also be equiangular. All three of the angles are 60 degrees. So there's no way that a right triangle can be equilateral. So that's a combination not possible. It can be isosceles if the two legs are congruent. It can't be a leg and the hypotenuse that are congruent, because remember, the longest side has to be across from the largest angle. So the hypotenuse is always the longest side of the triangle. It can never be congruent to a leg. So if you have an isosceles right triangle, it's because the legs are the same length. So that's possible. But it's also possible for all three sides to be different in length. Remember, with the third side, the hypotenuse having to be the largest side. So we can classify right triangles as either being scalene or isosceles, but not equilateral. So how can we use the Pythagorean Theorem? Well, remember, it can only be used on right triangles, and it is used to find unknown side lengths. Used to find unknown side lengths. It can be used to find a leg or the hypotenuse. But you have to know two sides of a right triangle in order to use the Pythagorean Theorem to find the missing third side. So you can be given both of the legs and use it to find the hypotenuse, or you can be given a leg and the hypotenuse and find the other leg using Pythagorean Theorem. So you use it to find unknown side lengths of right triangles, either the leg or the hypotenuse. So when we're solving for unknowns using the Pythagorean Theorem, we're often going to be getting radicals as answers, so they won't always just end up as being nice little perfect whole numbers. And so as a review, I want to look at how to simplify radical expressions, even though we've been doing that even recently. Now, I hope you recognize 225 as a perfect square. 225 is 15 times itself, and so the square root of it is simply 15. There's no need to worry about really simplifying radical expressions when they're perfect squares. But when we have the other three here that are not perfect squares, you have to be able to break that number under the radical, which we call the radicand, into two factors where one of them is a perfect square, so that you can take the square root of that number and bring it outside of the radical. Now, if you don't know all the factors, which most people would not, of every single number, you can use your graphing calculator. I know it says without a calculator, but I'm going to show you how to use your graphing calculator to help you find those factors. So whatever number is under the radical, you can go to your y equals on your calculator, put that number divided by x, and then look in the table. So go ahead and go to the y equals of your calculator and put 48 divided by x. So 48 divided by x. Remember, I went to the y equals to get there. So the table's in blue above the graph button, so you're going to have to hit the second key to get there. Now my table and your table may not be starting with the number 1 right here. So if that happens, you can just, press the arrow key over and over until you get there. But the easiest way, if you'll see you have in blue, it says table set above the window key. So if you go to second window, you can tell your table where to start. And so I usually like my table to start at 0. And so now when I go to the table, second graph, it'll start with 0. Of course, there's not anything you can multiply 0 by to get 48, so that's why it says an error right there. So these are all numbers that multiply to get 48. 1 times 48, 2 times 24, 3 times 16, 4 times 12, blah, blah, blah. Okay? I'm looking for perfect squares. So remember the perfect squares, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. Those are the perfect squares. I'm looking for one of these numbers to be the factor of 48. Now 1 is not ever going to be helpful, because if I separate 48 into 1 times 48, I have not changed a thing about my radical. So never use the 1 as your perfect square factor to simplify a radical. 2 and 24, neither one are perfect squares. The next factor pair are 3 and 16. Since 16 is a perfect square, that's the one that I'm going to use. That's the factor pair I want. So I'm going to think of 48 under the radical as 3 times 16 instead. Now I haven't simplified it. I just rewrote the 48 under the radical as 3 times 16. I'm going to circle the one that's the perfect square. I can't take the square root of 3 and get a whole number. It's not a perfect square. The 16 is, though. What number times itself is 16? Well, that's a 4. So when I take the square root of 16, it comes outside the radical as a 4. Now the 3 is still stuck under the radical. So this is set to be the simplified radical for the square root of 48. If you simplify it correctly, you can test it in your calculator and make sure that you've simplified it correctly. If I put the square root of 48, so second x squared, and the 48, and get it as a decimal approximation, I should be able to put my simplified radical in my calculator, and it gives me the same exact decimal approximation. So since I got the same decimal for both of those, I feel good that I simplified that radical correctly. So let's do the other two as well. So we're going to go to our y equals, and instead of 48 divided by x, we want 54 divided by x. We're going to look in our table. Remember, we're looking for perfect square factors, not 1 though. 2 and 27 are not perfect squares. 3 and 18 are not. We definitely don't want decimals. The next one is 6 times 9. Since 9 is a perfect square, that's the factor pair I want to change 54 into. 6 times 9. 9 is the perfect square. What's the square root of 9? 3. So the 3 comes out. The 6 is stuck under. So if I check that, the square root of 54 as a decimal and 3 square roots of 6 as a decimal are exactly the same thing. So one more, 135. If we go to our y equals and put 135 divided by x, look in our table. We're looking for perfect squares. This is a decimal. 3 times 45, neither one of those are perfect squares. That's a decimal. 5 and 27 are not. We get a decimal, decimal, decimal. Here we go right here. 9 and 15. Which one's the perfect square? The 9 is. So I'm going to circle the 9. It comes out as a 3. The 15 is stuck under the radical. So again, I can check that. The square root of 135 as a decimal and 3 square roots of 15 as a decimal are exactly the same. So again, that's just a review. That's some algebra skills that hopefully you remember. So the Pythagorean Theorem is one of the most useful theorems that we use in geometry. we're going to actually look at a hands-on proof of Pythagorean Theorem and why that works first of all. Now, I know a lot of you have memorized Pythagorean Theorem as a squared plus b squared equals c squared, but it's really important that you understand what that means. So remember, Pythagorean Theorem is applying to a right triangle. So we have a right angle in a right triangle. The legs are what we usually think of as the a and the b value in the Pythagorean Theorem, and then the hypotenuse is the c. So when you are looking at a squared plus b squared equaling c squared, what you really need to understand is that you're talking about the square on the hypotenuse is equal to the sum of the square of the legs. So that's what I want you to put on number 2 in your notes. When it says to state the Pythagorean Theorem in words, I want you to understand it means the square of the hypotenuse is the sum, that means to add, of the square of the legs. I'll say that one more time. This is number 2 in your notes. The square of the hypotenuse is the sum of the square of the legs. So that's really important, not just to have it memorized as a squared plus b squared equals c squared. So it also tells you on number 2 to use an algebraic equation, which that's what that is. That's your algebraic expression, or equation, I mean. I want you to be able to say it in words as well, though. So in number 3, this is where you're going to use your patty paper. This is our hands-on proof of the Pythagorean Theorem. What I want you to do is use your patty paper, and I want you to trace the figure that you have on your note sheet, okay, because we're not going to cut up our actual note sheet. So really, I traced the whole thing, but really the only parts you need are the shaded parts. So you need to trace these 2 squares and make sure you put the lines inside when you're tracing as well. It's also helpful if you number them the way that I've numbered them, so that you can see if you put yours together correctly. So I just went clockwise with the top one being 1 here, 1, 2, 3, 4, and this one over here I labeled as number 5. So I'm going to stop the video so that you can get those traced. And once you have those traced, the next thing I want you to do is to cut on the lines here, so you'll have 5 parts. And I want you to use those 5 parts and try to fill in the square that's on the hypotenuse here. So these 5 parts should fit inside that square right there. So once you have that done, you can start the second video.